Okay, now I started recording. So we're going to pick up where we left off last Tuesday. So make sure that everybody has their data read into your current R session. You make sure you set your working directory and label your data as assay just so you can keep following along. And then make sure you set your rep, treatment, and soil and year to a factor using any of these using as factor or the ordered function. As long as they're factors, we should be okay. So like I mentioned, we're going to be doing a lot of stats today, but before we jump into the stats, I wanted to kind of go back. We started talking last week about using table extra for tables and using R statics for some statistics. So I'm going to kind of combine the two and show you how to adjust some of these plots to make them a little bit more visually appealing. And so if you have assay, I don't want to mess up assay. So a lot of times when I bring in my main data, I want to keep it that way. I want to have it set, and I don't want to accidentally change something that messes it up and then have to reload it in. So the first thing we're going to do is make another data frame identical to assay. We're just going to call it assay 2. That should keep everything, ordered factors, everything the same. It's just that if we end up messing anything up, we can just reload it from our original data sheet or data frame. And just for the visuals of it, I'm going to create a new column in our new assay 2 sheet. And we're just going to call this all treatment. So we're going to combine all of our treatments together. And we are going to paste our column year, assay 2 soil, and assay 2 treatment. And I want to separate those out using, we'll just do the semicolon. What did I do? Oh, assay all treatment, assay 2, assay 2. Paste. Why did that not work? Oh, September. Oh, no, that's still not working. Okay, so error exists. Do I not have something loaded in? This was just working for me. It's embarrassing. Say 2. That's not. What did I do, guys? Assay 2. All right, now that one worked. No, I'm getting error exists catch key. Sometimes this happens. I don't know why this happens to mine. I'm just going to restart R again.
One thing I've learned, confirm this for me, if you like try to run all, but when your chunk having error, it stops at the error and it doesn't go anything.
Yep. Yep. And that's what's nice. So if you get that error and you look down on the bottom here, it'll tell you what line it actually stopped at. So it's really nice to get that. Okay, assay 2. Okay, now it worked for me. I don't know. I just restarted my R. So essentially what happened, we created our new data frame, and then we created this new treatment here that has all of them individually. So now instead of having like them all nested within each other, now we just have, what is it? 2, 4, 8 or 6 treatments listed out. What I want to show you guys is a lot of times in from publications and things, it's really nice to order everything like in the highest on one side to the lowest. That way you really get to see that distribution. So we're just going to manipulate our plots and order it by mean. One second, I'm gonna take this. I'm just gonna pause recording really quick. I gotta take this from Ryan. Okay, so sorry about that. Anyway, so we made this new one, and all I was saying, I just want to show you how to reorder. It's really, really simple. I'm just gonna say, once again, we're calling assay 2. So it's kind of like doing that ordered function in a way. But we were gonna call, so we're saying take our all treatment column in assay 2, and we're gonna say with our assay 2 data, we are going to reorder our column all treatment. And I want if we did just AF root rod index, it would do the lowest to the highest, but I want it the highest on the left-hand side. So I'm just going to put a negative in front. And we're going to sort reorder by mean. Okay, so why is it doing this? I'm just going to, is anybody else having this issue? Invalid. Okay, then give me, I am struggling today, I guess. Restart off. I am going to just take all of this again. What else are we using? Library. I hate that, but no problems. Okay, I'm going to clear all this out. I'm going to clear that. Okay. Starting over. Okay, perfect. So you don't really see anything when you do that reorder. But now let's just make a super simple box plot. So we're going to do GG box plot. So make sure you have the GG pub R package downloaded. Okay, I do. GG box plot, assay 2 on the x-axis, we are going to do all treatment. And on the y, we're going to do AF. And let's just do that. Okay, so now we can see everything. All I just wanted to show you is just how that ends up ordering everything. I know it's really hard to see. We can always do theme, axis, x, angle equal. Oops, that's not what I want to do. Element.
My graph does not look like it.
Oh no.
It's just kind of like descending.
Yeah. Oh, okay. So did you run this reorder? There you go. Okay. Very nice. So yeah, Mike, you've learned out firsthand then what it looked like before reordering. And once again, so if we wanted to reorder it the other way, we can take out that minus sign up here in AF, run that the other way. So now we have all of our treatments with the lowest on the left going to the highest. So especially with a lot of data, it's really nice to be able to visualize this a little bit differently. And I will mention that these box plots, I should mention, this line here in the middle is actually the median, and then we have our interquartile range, so our first and third quartile. And so once again, it's always a good idea to add in our actual mean. So that once again, we use that summary function, stat summary function equal mean, and we're gonna do geom point, and we're gonna do shape. It doesn't matter what shape you use. I'm just gonna use shape 1. There we go. So those circles are the actual means. So you can visualize it a little bit better. Sometimes it looks funny because like the median is a little bit higher. So having those means there actually show you. So you get a good idea of the distribution of the data and the order of them. Okay, you guys got that? Pretty simple, right? So it's just one line of code. You can always do that. And you can do it to your normal data frame. I was just afraid of messing something up. So, and I wanted to add in that extra column. So now next thing I want to talk to you about is for publication or for, creating figures and even stats. I am very hesitant to do this, but if you need to drop any outliers to kind of manipulate your data, maybe to satisfy some assumptions, or you just know that those outliers are from, some sort of damaged plot. Maybe you had deer eating your sugar beets or something, or geese. We got a lot of geese eating sugar beets. Okay. So first, I just want to visualize our outliers. So actually, let me just title this. This one was ordering by means. This one, we're going to do dropping outliers. Okay. So first, let's just visualize this. We're just going to do ggboxplot again. We can use our original data frame. I don't care. Now, what you're going to notice, I'm not even using an X variable. I just want to plot all of my data in one spot to look at that distribution. So I just want to look at, actually I have more outliers than rise. So we're just going to look at the rise root rod index. There we go. So in like ggboxplot or ggplot or ggpubr, an observation here when it comes out as this dot is an outlier. And they're defined as an outlier if it meets one of the following 2 requirements. So the observation is 1.5 times the interquartile range, less than the first quartile. What? Maybe I missed a period somewhere in here. Observation is 1.5 times greater than the interquartile range, or maybe the observation is 1.5 times the interquartile range. Oh, greater than the third quartile. So either can be above or below. That's what it's saying. If it's 1.5 times that interquartile range. Okay. So you can see here, if we just straight up counted this, we got 1, 2, 3, 4, 5, 6, 7 outliers is what it's saying. So let's just go ahead. If we wanted to remove that just to see how everything would look, the first thing we're going to do here is actually this dim. This just shows our dimensions. So this is showing that we have 48 observations among 11 columns. So essentially we have 48 data points in our data here. Once we drop our outliers, we can use this dim function to make sure that we've dropped out the 7 outliers. So that just helps you know how many you have. Okay, so first we have to set up and we have to figure out what are the quartiles in our data. So I'm going to name this quartiles and use this quantile function. We're going to say assay rise RRI. This quantile default, I don't know what probes mean. And we're going to do the first and third quartile. And just to make sure, we're going to do NA. So NA remove equals false. I don't want to remove any data at this point. We're just setting out our quartiles. Okay. So that gives us this value. So 0 and 14. And then we're going to figure out our interquartile range using this IQR assay rise RI. Okay, so that gives us our interquartile range. And now we have to set our lower and upper limit. So that 1.5 times quartile. So our lower limit And now we're calling that first function. So in where we made quartiles, and then we're going to call our very first value within that quartile. So once again, our first quartile here. So, and then we're going to minus that 1.5 times our interquartile range. Okay, so now we set our lower limit, and then we are going to set our upper limit. Oops, I want 2 on that one. And we're going to do plus 1.5 times interquartile range. Okay. Now we're going to make a new data frame. Just bear with me. This is going to be a long name, but I'm going to say rise, root rot, index, no outliers. And now we can finally filter. We're going to use that filter that we used before. We're going to take our assay data, assay, rise. If it's greater than, how does this work? Yeah, greater than the lower limit and assay, rise, root rot index, less than, oh, whoops, ampersand, and greater than upper. Okay, what does that?
Oh, you got 2 brackets.
Yeah.
And then it's saying upper is not found.
Must be a size of 48.1. How did I do wrong? Why is everything doing this?
Is your upper not found either?
Filter. Let's see. Root rot index. Okay, just double check everything's spelled right. No, mine, that worked. So just make sure that everything looks the same. Make sure everything's capitalized or it needs to be capitalized. So now you can see, we can do it both ways. So you can look up here in your environment. So now my new data frame only has 41 observations. That means we dropped out 7 of them. And those 7 came from, those outliers there. So we can also use that dim function. Oops. And you can see that we only have 41 observations there. And just to visualize it, plot, rise, root rot index, no outliers. Y equals rise, root rot index. Hey, Sam. Weird. Okay, so it's still, even now with our new data, we still have 1 outlier, but you can clearly see how it kind of manipulated some things. So, like I mentioned, I am very hesitant to do this, and only if you have sufficient evidence that these are true outliers or you have an immense amount of data that you need to clean up, only then it would be acceptable, I would imagine. So do this very hesitantly. I'm just trying to think, like maybe in terms of like weather data, you can also use this to figure out, well, what if you had something like it wasn't recording properly and during the summer you got a reading of 32 degrees Fahrenheit? Like, that's not right, right? So you can kind of use that as, looking a little bit deeper, like, oh, am I missing something? Did something get misentered or was there a malfunction? Then you can go back, and if you have that data and you can't replace it, you can just take it out. So you can mention, you dropped out temperature from July 13th due to misreading.
There you go. We were just talking about that.
Really? Mind reader? Yeah, I remember that.
2 February and 1 July.
Yeah, but the rainfall? I don't know, you had some rainfall missing. All the days. Really?
My box plot looks exactly the same.
Oh, you didn't change anything?
Back there again.
Okay.
Oh, no.
This is the new one.
Yeah.
I'm talking about dropping outliers, Sam, if you didn't catch that.
Yeah, I was trying to think of, you know, like, I learned a specific line code to test for outliers.
So, you know, and even if like all you have to do is just actually do a box plot.
Yeah.
So you can clearly see that you have 7 outliers. And so if you do want this is how to kind of manipulate. So you're making your own quartiles, interquartile range, and then subsetting your data based off of that. Okay, moving on. We're going to change gears now. So I just wanted to kind of throw that in there, you know, because we were working with plots and then started talking about some stats. Now we're finally going to transition into straight up regression models, doing ANOVAs, analysis of variance in R. Oh, actually, I'll just go up here. ANOVAs. This time, let's just right away. Oh, I guess no, we don't need to do that right away. I have a bunch of other ones. So everything that's a straight up ANOVA, like the simple general linear models are in your base package, so you don't have to have anything special. And I just want to show, you know, what a simple one looks like. So I'm calling this a model. We can bring it in later on. We're going to call this AOV function, and we're going to create a formula. So I want to see if AF root rod index to a tilde is significantly different between treatment or soil or treatment, or if there's an interaction between soil and treatment. Now, if you run that, and then at the very end, data, you put your data equals calling from assay. Okay, so now we have model up here is just this list. So to summarize that into a table, we just do summary model. Okay, so now we get our ANOVA table down here. So we can see there's no difference between soil. There is a difference between treatment, but there's also an interaction between soil and treatment. Now, this is kind of a lot to write out. But what I want to emphasize here is that when you put the semicolon in your linear model formula, that is calling for an interaction. And there's a shortcut to do this. So I'm just going to do another one down here. I'm going to do model again. You can just adjust your first one too if you'd like. I'm just going to write it out. So AF, and you can just do soil with the multiplication symbol by treatment. Data equals assay. So this right here, the soil times treatment, is identical to writing this out, soil plus interaction. So it's a lot easier to write that shortcut. So I'll just run that and show that they are the same. All right, so now this was the output from the one with the pluses. And this is the output with the one with the multiplication. So you can see they're exactly identical. It's calling all the same functions. So that is a super simple general linear model. But you know, a lot of times we are, and like the research that we're doing randomized complete block designs, not completely randomized designs. So we need to add in a blocking factor. So, and I will say most of the time, this is just a CR completely randomized design with no blocking structure. So now we're going to do another model. Oops. And I guess I'll do that. Randomized complete block design. Model. Oh, we'll get used to writing this, I guess. AOV, root rod index, and tilde again. And now we want to add in rep. So our rep is our blocking factor, and we still want to be looking for those interactions or main effects. Oops, data equals assay. And then we're going to do, summary model. Okay. So now you can see that we added rep in there, and this will also change how we calculate some things. So now you see that our F value has slightly changed for soil, changed our P value a little bit. Same things with the interactions and other main effects. And also changes our residuals as well. So once again, adding that blocking factor is changing our overall model to better represent the randomized complete block design. However, I think at this point, yeah, I should just emphasize that this is not a mixed model, right? So this is still a general linear model with a blocking factor. So there's a very important difference between running mixed models and general linear models. Right? Okay, let's go ahead. We're gonna load in this other package. I like this package. It's called Agricola. It's really hard to spell. Agricolae. You guys have to install it. Sorry, I'll do that. Install packages. Agricolae. And just so you guys see, Agricolae. Oh. There we go. So agricolae package is a statistical procedures for agricultural research. Imagine that, right? So, a lot of these, so what is it? So you can use this for planning a field experiment. So it like helps you do like the randomization of your reps and things like that. But mainly what I'm using this for is the Fisher's least significant difference or Tukey's honest significant difference. You can also use a lot of these other post hoc mean comparisons. You can also do non-parametric tests like the Kruskal-Wallis analysis of genetic experiments. I didn't even know that.
These are all created by somebody, right?
Yes.
How can you trust that?
I mean, that's a good point. He's a statistical engineer, right? So, I mean, they're also, I wouldn't say, are they peer reviewed? How does that even work? When you put something on CRAT, like.
I would say the thing about these is statistically, there's only one way to do a group cell bond. But so the onus is on you to make sure that the data that you're giving it fits the assumptions that it's asking. So for a generalized linear model, there are specific assumptions that go along with it, like normality.
Yeah.
So the onus is on you to actually be giving it data that should be run by that in specific. So when I took statistics in my master's, like we had basically a flow chart that was like, is your data normal?
Yeah.
Yes, here you're like, and so you kind of go down. But the test is run the same in our, like I personally like the first walls, that's right. The actual statistical test would be run the same in SATs or not. You get basically the same p-values.
Almost basically.
Almost basically, they're round differently. But the onus is on you to say, my data should be allowed to run it better. It will not check those assumptions for you. You have to do it yourself. Yeah. So when I took stats, you would have to say, and here's my QQ plot, and here are the assumptions that we met over the year.
Yeah. So we'll get into that. That's my next section. But yeah, these statistical models were developed decades ago, right? There's only one way to really do these models. So, and there's a lot of different packages that can attempt to do it. However, I just like the agricolae because they make it a lot more user friendly, right? So all of these are, it's not like this guy's coming up with this brand new way of doing a strip plot or Kruskal-Wallis. They have developed these packages to do the statistical models based on the formulas developed decades ago.
By Kruskal and Wallis.
Yeah.
And now they're actually tests that can be done. Whereas before, computationally, like you couldn't do them by hand. You needed a computer to do them. So they are like comparatively new, but they're like actually doable in a way that they weren't previously. But the stats is the stats.
Okay.
When you go into this and you present on this stuff, you have to use this as a reference. This is what I used in R.
Yeah, exactly. So when I'm writing, I will say, this is the package I use. This is the version I used. These are the adjustments I made. This is exactly how I used this package to get the data that I had. I did not meet the assumptions of normality, so I had to perform a log2 transformation to resolve model violations, right? So I have to say all of that type of stuff. so people understand, what's happening. Anyways, so agricolae, what I really like using it for, even when you have base models, is it really easy to do post hoc mean comparisons. So let's just do, once you have agricolae loaded in, you can use this LSD.test. Super simple. Now we're going to call our model that we created, right? So model is our output from our general linear model. And I just want to compare the treatment. I don't know what it's TRT. Treatment equals treatment. And then we also want to add console equals true, because if we don't put that, we're not going to get the output. So finally, this is where this comes in. We get our least significant well, actually, I should point out this alpha is our significance level. So we're at our 0.05 significance level. Those are our degrees of freedom for error, critical value of t, and importantly, our least significant difference. So Mike, you're talking about least significant difference. And then finally, it does the letter groupings for us, which is really nice. So it shows us the mean for Cabina and also shows us our letter grouping. So based on our ANOVA output, we know that there was a significant difference between treatment. And based on our post hoc analysis, we can clearly see they belong to different letter groupings because they are different enough based on our least significant difference. Excuse me. But we wanted to look at the interaction because we do have an interaction. It's fairly similar. We're going to do treatment equals, but then we're just going to put in our, our little C function there. So soil and treatment. Sorry if you can't see that. Oops, console equals true. Okay, so there it does the same exact thing, but now comparing our interactions as well. And very easy, if you don't want to do Fisher's least significant difference, we can just change that to HSD. This does Tukey's on a significant difference test. Sometimes there's some difference. Fisher's is, I don't know, this is why I wish Joachim was here. He would be able to explain it a little bit better. Tukey's is more conserved. So a lot of times you will get a narrower range of letter groupings where Fisher's is a little bit more lenient. They can say, yeah, I guess there is a difference there, where Tukey's would say, not really. So there's different ways of approaching it, and that's up to you to decide what's the best for your research. So as Sam alluded to, though, a lot of this comes with the prerequisite that we're meeting assumption, right? And so how do we test for assumptions in R? So I'm going to go through, I have like a lot of data here that you guys can, or a long list of information for you that I'll send out with my notes that talks about the normality of residuals. We talk about homoscedasticity or constant variance. And then I also discussed two different ways of testing for a homogeneity of our variance, such as the Levine's test, which is a non-parametric test. And then I'll show you how to do this Bruch-Pagan test, which is for a parametric, is a parametric test, mostly used for the regression analysis. I don't know. It depends. I really don't know. Once again, I wish Joachim was here. Maybe he could talk a little bit more about this. So there's quite a few different things we can do, but first we should load in and install two new packages again. The first one is mass. Oops, you might have to restart. I shouldn't have done that. I'm just doing this for you guys. Install packages. And the second one is R. First one's all uppercase, second one's all lowercase. Oh, sorry. There it goes.
Restart.
Sometimes. Okay, and I'm just curious. So mass stands for fine. Except for Venables and Ripley's mass. I can't remember which one this was for. I can also do box cock transformations for linear models. I know there was one time I was like going through, I'm like, I don't even know what I'm using mass and car for. So I deleted them out of my like library. And then I ran everything and I'm like, oh, it's for all my assumption testing and stuff. So I don't remember what exactly these call for, or what is calling on these packages, but mass and car are used to test assumptions. I can tell you that. Okay. The first thing I like to do is just look at the distribution of your data. We can do this two ways. One is using this GG density plot. And let's just look at AF root rod index. So you can kind of see that our data is a little skewed. We have a lot more data here at the higher end. Typically, this should be following that bell curve, right? And we can also look at this using just a histogram. So there's almost the same exact things. Histogram, AF root rod index. Okay, so there's our histogram. Here's our density plot. Very similar. It's showing that we do have skewed data. So odds are when we run our assumptions, we're probably going to violate some.
You gotta reload.
Oh, that's how about you guys? Do you guys get these packages loaded, or are you guys having to restart and redo everything? Yeah.
Which one do you mean? GG box plot? Or GG what? Which one? You got bot or GG pub R?
Well, I don't know if I'm doing a lot more. Yeah, I might as well. So just do these ones right up here. And then I'll just go ahead and type it. Library, agricolae. And we're also going to do math and car. Those are all the ones that we want. Do you know what I've got planned for this weekend? I'm going to create a loop so we can do a general linear model just like Proc GLM in SAS. That's what I want to do. You know how you just, because like when you run GLM, you can just write all like 10 variables and it will go through and give you everything. Right?
Oh, you want to mimic that in R.
I want to mimic that in R instead of having to do it individually for each variable, right?
Yeah, that's when you're deciding between R and SAS. The benefit of SAS is that it runs everything it could possibly do.
Well, and that's when you do GLM though.
Yeah.
If you're doing proc mix or proc limix, you have to specify every variable individually. So it's not really a benefit. You can't get glimix to run all of your variables at once.
Oh.
Because I don't think so. Like when you're going through and you need to do like the letter groupings and everything after glimix, you have to specify them all individually. So you have to have a chunk, essentially like a chunk for root rod index, another chunk for.
I just list them separately and run each.
Really?
Yeah. But
I've never
I use
figured that out.
I don't have it on my computer. You can't put it on one.
Really?
I tried to. I have a web version as long as I still can pretend I have a UW license.
Okay, so everybody got those loaded in. I'm just gonna go through. We're gonna flip through quite a few of these. I just want you guys to have these available. The first one that we're gonna do is actually we have to set up a model, and I'm gonna kind of try to do this a little bit more. So if our first model here, we're gonna do analysis of variance, root rod index. We're gonna look at the interaction of soil and treatment again. And this time I'm gonna do my blocking factor as the interaction between rep and year. So it really increases our degrees of freedom. It's technically, yeah, we'd have like 12 for each one. So rep and year are our blocking factor. And like Sam alluded to, why do I always forget this? Data equals. Okay, QQ plot. And we're just gonna call our model again. Is this really not gonna work? Oh, QQ plot needs to be capitalized. There we go. I'll show you another way to do a QQ plot. That's just straight up calling QQ plot. But okay, so just so you guys know that running this, do I have the information? Running this on the model Oh, where did it go? QQ plot. Okay, never mind. Let's do it above doing model. So if we do QQ plot and we just do assay AF root rod index. Okay, we're gonna get kind of similar here, but you see we're trailing off a lot. So what this is doing is the quantile comparison plot of the empirical quantiles of a variable. So just AF root rod index. But when we call model and we run our model and then do that, do the same one, you see that we're not trailing off so much. This is actually plotting our studentized residuals from the linear model. So they're calling two different things. So depending on if you do just your variable or you're actually calling on the model. Because, you know, when I did this model, I'm also blocking by rep and year. So it has a little bit more understanding of where those differences are coming from. Generally, when we're looking at these plots, we want them to either fall on our plotted line. We want them all to be kind of in line. All right, so the more, if we go back to our other ones, we see that we're really trailing off this line here. These are suggestive of our outliers. Oh yeah. Another one that we can do. So now finally we are going to get into.
So can I see the other way to do QQ plot?
Are you just talking about just doing plot model? Yeah, I'm getting there. I got like 7 of them. So before we get into all of those, I'm just going to go through these tests. So the next one that we're going to do is our test for normality. And typically the Shapiro-Wilk test is standard, I guess. So we're going to do Shapiro-Wilk test, and we're going to call the residuals from our model. Okay, so it's nice, even though that we had some of these, you know, trailing off things, this is saying within our model, we do have normality. So that's kind of good. Well, what about homogeneity of variance? Right, so this one, Levine's test is a common one. We're going to call the one from Carr Levine's test. And now what's really weird about this is that these have to be completely cross formulas. What that's meaning is we can't add blocking factors. So this is just seeing what our homogeneity variances without blocking factors. Data. Did that even? Maybe we can't do this. Maybe you have to do the LM function, linear model. Okay, so instead of doing AOV, LM and AOV operate the same. But within Levine's test, you have to use LM for linear model rather than that AOV for ANOVA. So a little different. It's kind of a pain. So we run this and we're like, oh shoot, we are violating our assumptions of homogeneity.
Where do you see that?
So our p-value is less than 0.05. So we reject our null hypothesis of homogeneity.
Okay.
Homoscedasticity. Homoscedastic. So our data is heteroscedastic, meaning we don't have to get into that. Yeah. Okay, well, let's just see, and I don't know if this is appropriate to do, but let's call that Bruce-Pagan test. See if we get the same thing. So we're going to call the Bruce-Pagan test. I'm just going to copy that same formula. Darn, that's also calling us, or also violating assumptions. So really quick, no, we're not getting there yet. We're going to talk about these other plots. So there's other ways to look at this. So like, well, is it really that bad? Is our data really that not homogeneous? So we can call these plots. We're going to call plot, and I like to do it this way where I'm just calling plot 1. So we have this residuals versus fitted values. Once again, you want to see this almost as a straight line. So we're seeing that we do kind of have some what do you say? Yeah, sure, weirdness in our data. So let's just do our model 2. And actually, I can't remember. Right, that's our QQ plot. So that one should almost be identical to the QQ plot we called up here. I just like that this one kind of has those confidence intervals on it. But I mean, you are calling it with those standardized residuals. Then we have the scale location one. Can't remember similar to the residuals and fitted plot. So this is our model 3. All right, same thing. We kind of have some tailing off going on. Cook distance is our next one. A lot of times this is like when you're seeing these values kind of off onto the distance, this is also calling out those outliers. Same thing with Cook's distance. It's kind of weird. It's like a measure of the influence of each individual data point on the total. So essentially these ones that are super high, these ones have the strongest impact on the variability of our data, right? It's suggestive of outliers. Once again. Okay, last one. I don't like doing the sixth one. Plot 5, constant leverage residuals versus factor levels. So we're kind of doing that same thing as 1 and 3, but now we're separated out between our climax and pearly soils. And what did I say here? So assess the presence of influential, oh no, that was the other one. Assesses the presence of influential observations or outliers within each level of a categorical predictor variable. It's confusing, but that's just what I read. So once again, generally all these plots, those lines should be generally straight without calling these outliers.
And if you just do plot, like model, and you don't say a number, it'll just tell you what's really.
Yeah, but what she's saying is if you just do plot model, right, it comes up, but then like it's just frustrating because
Each one, there's multiple.
Yeah. So you can kind of go through and kind of hit everything. But when you knit it, it will all come out together. It's just a pain in the butt when you're actually running the code because it's making you click through everything. And I don't think 1, 2. Okay.
5.
Okay. Yeah. Oh,
Sometimes it does, sometimes it doesn't. But
Yeah.
sometimes I'll put them into 4, you know.
yeah. That's why I like actually calling them out and then I can go back and look at it. So yeah, really quick. I'm just going to show you this. So it's super easy to do transformations. I'm just going to show you one really fast. I'm like, all right, so we know that we're violating our assumptions of constant variance or homogeneity of variances. So let's just see if we run a new model, but we are doing a power transformation. All you have to do is call AF root rod index. I'm going to raise it to the power of 3, or we could do like the log base 2 of AF root rod index. So that's all you really have to do to transform that data. It's super easy. The log transformation makes it so much worse. I've already tried this, so we're gonna do this. I'm sorry. I was just showing. I just want to show how easy it is, and we're just gonna do treatment, soil, plus a blocking factor, the interaction between rep and year, calling from our data assay.
Does it matter if you took all the treatment?
Nope, does not matter. So Mike asks, is there a difference if you do soil before treatment or treatment before soil? No, it'll do the same exact thing. And you can also put rep and year in front as well with that plus. It really makes no difference the order that you're putting it in. Unexpected. Oh, I didn't put AOB. Got to call that. And then if we did like the histogram, we could have done this first. So, if you wanted to go through a couple different types of transformations, you can kind of just look at the histogram here. So, we kind of are evening out a little bit more. So we're kind of getting more weights on the bottom. But just check out if we ended up doing it this way, we do log base 2 of assay root rod. Okay, so you see when we did the log transformation, we're not making anything better. We're still really weighted on the one end. But when you do that power transformation, we kind of get a little bit more equal things there. And we can just kind of go through just for the fun of it. I'm sorry, I am going to copy and paste, make it easier on me. So once again, now if we go through and we do Shapiro's test, All right, we're still meeting our assumptions of our normality. We're gonna go ahead and cube that. Yeah, there we go. So now we pass Levine's test for homogeneity. We also are passing Bruce-Pagan's test. So, and then we can kind of go through. We've already called our model. Didn't really help that one out. I don't know why that one's still so tailed off.
So how did you figure out that it was a power of 3 is something you could get?
Yeah, this is what, when I do this over the weekend. I like doing log transformations. I was going to try to show you how to do a Box-Cox transformation, but it doesn't like this data because I have a lot of zeros in it.
I will add a comment, which is when I was during master's, at Wisconsin, they have like statistical advisors, so people who are doing masters or PhDs in stats have to do like a help desk essentially. And my stats professor, our class was plant pathology, forest and wildlife ecology, entomology, and plant breeding students. So like all plant people. My professor in front of the class said, I hate plant pathologists. I hate the way you guys do research. And he hated helping us at the help desk because we don't really fit normality and randomness in the way that pure stats would like you to. Because you are limited, you can't like mix an inoculated plant and a non-inoculated next to each other. You know, like that's going to work. So we end up having to do funky things with our stuff because all of these models are built off of a perfect system that is not practical for a biological system. So that's why over time we learn like what makes sense, because just the way that plant pathology or even just plant experiments in general run means that you're never really hitting a perfect normal randomized equal variance thing. It's just not like realistic. However, that's the easiest models to make. So those are the common models that exist in the world.
And we'll kind of get into that a little bit more. So even like agricultural research in general, when's the last time we had like 2 consecutive years that were identical, right? It is unbelievably wildly variable, right? So look at data or Yoakum's data for wheat, like yield. So now you have it split between 7 different locations, north to south. Some are dry, some are super wet. You know, how do you handle that? You never have like really good normality because you don't have normal.
The summer took her master's program because her first 2 field teams were so opposite in results.
Yeah.
That they needed a 3rd season just to like be able to say anything. So the point was just that the help desk, my professor passed it off to a grad student because he hated working with the pathology students so much. So
Yeah.
he was like, I hate the way you guys do that.
So, but yeah, we'll talk like how do you make those decisions later on. So let's go ahead and take a break. When we come back, I'm gonna touch on split plot designs, split plots, and strip plots. Super simple with Agricola. And then we'll talk a little bit more about calling in the LMER test or LME4, which is generally like if you go for us like plant disease. I don't know, Danielle, if you like submit being with FHB, if you're submitting to plant disease or anything. They almost require you. It's like right in the manuscript preparation, letter to authors. If using R, you have to do a mixed model using LME4.
Yeah.
Essentially, like it says flat out right there. Now, I'm making the argument, technically, when we do these split plot designs, Agricola, when we set this up, when we come back, it is a mixed model and our blocking factor is considered random. So it is a true mixed model if you need to do split plots. But it's just not with the LME4 package. Now, I just went through reading. So I looked at all the split plots. In R, there was 7 different papers, all with a different way of analyzing the split plot. It was ridiculous.
You can really get bogged down in tech. It was very common.
Anyways, I'm going to stop recording now.
To get a minor during your plant pathology PhD in STEM because it was so.
Okay, resuming recording. So we just picked up with just doing some straight randomized complete block designs. I just want to introduce some split plot designs because it's super simple with Agricola. So hopefully you have Agricola loaded in. Once again, I'm just going to keep calling it models, just easy enough. This is a little different. We're going to call with, and we're going to say assay this time. So we're putting our data first, and we're calling split plot. Let's just do rep as our blocking factor. And then we're going to put soil. The one that you put first will be our main plot. The one you put second will be our subplot. And then we're looking at AF root rot index. So if we go ahead and we do help split plot here, split plot with agricolae, this is a typo. They still have not fixed it over the last 3 years. So here it shows the split plot with the blocking, replications first, the main plot, our main plot factor, and subplot factor, and then our variable and response. Oh, you know, and once again, let's just assume that these are split plot designs. And technically I could think of it as like a nested design is another way of doing like a nested design, because each of these treatments are nested within soil. I don't know, you can maybe make that argument. I don't know. But we're just assuming this is a split plot. Okay, so we can run our model and it pops out right away. We don't have to do the summary or anything, but it will show us our rep, you know, so no difference. Our soil, there is a significant difference for soil now. Treatment, no significant difference, but there is also an interaction. But you guys need to keep in mind, so the reason why split plots are so different is because within our main plot, we actually have a different degrees of freedom. So this EA here is our degrees of freedom for our main plot, and this EB is our degrees of freedom for our interactions and also our subplot. So it calls it very differently. So we have to, before we do any like the Fisher's least significant difference, we have to call those values separately to bring them in. So we're just gonna kind of do that. We're gonna say GLA is equal to the model GLA. So let's actually, I'll show you this. So we open up model here and we get these numbers, this GLA, GLB, EA, and EB. So this is what we need to use for our post hoc, our Fisher's least significant difference. So we got to call those all individually. GLB, model, GLB, EA, model, EA. I don't know. Am I doing something weird? GLA, GLB. I keep getting these errors. EB, model, EB.
You're doing those backwards, you're calling it, I've been doing equal with this before.
Yeah, sometimes you can. What do you mean? Just do like you can just say equals?
Yeah.
I think depending on how you have it set, I did read, maybe you can do that. What is your take on that?
Yeah,
Processing of
I think because not always does equal work, and so.
Yeah, in certain circumstances.
It's not gonna generate the if I use an equal.
I don't think so. I think it's just, I don't know. I read it somewhere that somebody had done that. It's kind of like Darla's piping thing, you know?
That actually does have it.
Really? It's not
And
truly
they're
piping?
extremely successful.
Sure. Oh, I want to talk about that too. Like masking arguments through different packages and call like how to actually call a certain package.
But generally, like it's best practices, which is mostly just if you do it always the same way, you know, small things that don't matter, then you're less likely to make mistakes in big things you do.
Yeah.
Oh, it's
That's
like
like
here,
real-
will have eventually, so might as well always do that.
A model for life, wake up and make your bed every morning.
What did Oh, I did do it up here. Okay, sorry, I'm moving around a lot. I just wanted to see the difference between it. Because we got to call this a little bit different now.
You just gotta do GLA, GLB, EA, and EB.
Yeah, so we called those, but now when we do, so this is when we did our first LSD test, where we're calling everything. But you see here that now it does actually have our degrees of freedom error and our mean sum error, or a spot for that when we look. Maybe we can do it. I'm gonna try something. Just bear with me. I wonder if we can do this. So for our treatment, or actually we'll do soil first, because soil is our, now we can call our degrees of freedom error, which is our GLA, and our EA. I'm gonna see if this works. Oh, see, yeah, that's weird. Okay, so it's calling it a little different. So it doesn't give you a really nice output. That's not how it's supposed to. So I'm sorry, do not use that. I know, that's not. So this is the way that I do it. You have to call this with first. So we're gonna say with our assay data. Sorry, I just wanted to see if that works. We're gonna call LSD test. And now we can type in our AF root rod index or our Y factor. Yeah, we don't want to use model. We want to just kind of use this. And then we want to then call our degrees of freedom error and our mean sum error. And console equals true.
Yep, me too.
Yeah. What do you mean issue with assay? Anybody else?
Oh, mine works.
Really?
Yep. I don't know what I did though, so don't ask.
Oh, now it worked. Weird. Maybe I just had something highlighted. Okay, so you can kind of see, I don't know if we compare it to other one, if there's a difference, but just so you guys are aware now. Yeah, so once again, that was for our soil. So we got to go back up to our model here. So you see how soil is with our EA degrees of freedom. So that's our like main plot degrees of freedom. So if we call our, if we want to look at the interactions or the treatment, we now have to call our other degrees of freedom. So if we call treatment, we need our GLB and EB. Okay, so those are our treatments. And then same thing, lastly, I guess, for our interactions, we need to call, I think I always forget how to do this properly. Okay, so we can do it that way. Let me do this. Got it. So when we call model, you see how soil and treatment have that semicolon. So that's what we have to call with our GLB and EB console equals true. So there's our interaction. So super simple. If you do the split or strip plot, okay, so you can do a split plot just by doing SPE plot, and then you're adding in one more sub factor. Strip plot, I can't remember how to do it. It's super simple. It's very similar to this as well. You have your horizontal and vertical factor. So it's pretty streamlined, pretty straightforward. And once again, this is technically a mixed model and rep. So your blocking factor is also a random effect. And we can also do the interactions by year and rep as well, see if that changes anything. Yeah, now soil isn't significant if we block out by year. Makes sense. Yeah, I'm sorry. But once again, I just want you guys to be aware this is how you do it. I know this isn't supposed to be a stats class, but at least for Umera and James, this will be important. You guys will have to do stuff like this. Okay. Now we're going to finally get into mixed models. And so I mentioned this package before. Oops, library. You can use LME4, which is kind of the standard.
Try to be loaded in for us.
Oh yeah, no, you have to do install packages. If you don't have this. Did you?
No, why didn't we do it?
Oh, because I didn't want to bring it in. It'd be a huge list. But I also like to use this lmerTest. This is also a newer extension of the LME4 package. I don't really know the differences. There's not a lot of differences. lmerTest is just built on LME4. Maybe it can handle different things. I really don't know. Okay. And so this is for actually doing the mixed model, but we also need to call in or load this emmeans package. So the estimated marginal means, and this is identical to LSmeans, least significant means, like when you're doing proctolimics and stuff. So the way I would interpret this is like LME4 is proc mix in SAS. lmerTest is procglimic insects. Is a way to kind of compare them. Very similar, almost doing identical things. EMM means estimated marginal mean. Least squares means. Why am I saying least significant? Least squares means. LS means. Okay. So anybody, Mike, Darla, can you give an example of a random effect?
The weather.
Close. Soil type. Okay, yeah. So let's say, where would different soil types exist?
Everywhere.
If you were to put a column header on it, location, right? So when you're doing random places, location could be a random effect. Year is a random effect. Your replication or your blocking factor could be a random effect. I don't know, I'm trying to think of anything more. Okay, so what is a fixed effect? Umera, what is a fixed effect?
Treatment.
Perfect. Yes. So it's something that you also kind of have control over, right? So this is the treatment I'm putting in the ground. This is the variety I'm comparing, right? That variety most of the time is pretty homogeneous, right? It's not like there's going to be a lot of variability there. Now, unless you're Sam. Sorry, that was not the best example. No, well, the way sugar beets work,
More internal variation.
the way that with the breeding, you have a lot more, I don't know, you can probably explain it better.
It's supposed to just like, the most variety is more standard within. So like, if you look at it overall, all the individuals from the population are pretty close together. Whereas mine have a lot of internal variation in which every individual is very different.
Well, even look at like sugar beets. So once again, we were talking about the crazy difference in population. So in wheat, you're at 1.3 million plants per acre. Sugar beets, you're at 40,000. You go look at a sugar beet field. How many off types do you see? How many bolters? How many Swiss chard types? How many that are different colors, or the purple beets or red beet kind of colors? Or you have all these off types within a much smaller number of a population. So sugar beets, especially for Sam, working with pre-breeding lines that have not gone through that commercialization, there's just so much variability. So potentially you could call.
Inbred, I mean, in the high, every seed.
Anyway, so those are examples. So just think of like your treatments, varieties, things like that are fixed effects. Things like year, rep, location, those are your random effects. So let's go ahead. We're going to call one more model. And we're going to call, instead of using the LM or the AOV, we're going to do LMER. So you see how it's calling the lmerTest or LME4, if you have it. We're going to call, I don't know why I did that. Okay, let's just keep doing AF root rod index. The tilde compared to the combination or the interactions of soil and treatment. And this time we're going to create do this one and this straight up and down line rep. So this one is calling random rep random. That's essentially what it's doing. And that's really the only difference here. There's some other ways where you can call, like you could say the interaction of rep within soil. I think it's, oh, maybe not. Oh no, oops. Data. I'm just curious now. I'm just gonna play around for a second. Model may have converged. Okay, model failed. See, sometimes you can't do stuff like that. So let's just do one rep. Okay. So it is giving this modified, or this is singular fit. There is something, let's just see. Huh,
I can't even do the first thing.
what?
Function, coal mod factor, LBETA not provided by package.
Do you have the lmerTest?
Yep.
And you got this in, you got your rep in parentheses, this
Yep.
1+ data,
Yep.
LMER.
Yep,
Try not to use your equal sign.
I did. I think it's the
Oh, okay, arrow. Yeah, I don't know what to tell you. Anyway, so now that we have that, now we have to use this ANOVA. We can't use the summary. We're gonna say ANOVA model. And there we go. Now we get it out. And now you can see that we're doing this type 3 analysis. Once again, doing like the regular general linear model, you're doing type 1 analysis. So this specifically calls type 3 as well. Once again, if you ended up knitting this though, this table is going to look like crap. There's no way you're going to read it in your HTML file. So once again, calling what we did, last week, we're going to bring in our cable package and make it do the cable styling. Oh no, I don't want to do that one. Let me find a different one. Where did my other cable? There we go. I just want cable class. Yeah, that's the one. Yeah.
You always get the error.
That is singular.
No, our tools is required to build our packaging, but it's not currently installed.
That's a weird one. I don't know why I've gotten that sometimes.
I don't know. You might have to.
Yeah. I know once you get it all set up, it usually runs a lot smoother. So sorry about that. I don't think, I'm just curious. Once again, I'm just playing around. Does that work? Model. Right, degrees being 43. Huh. Once again, I'm just playing around at this point. I'm just seeing it. I was really hoping you would be here. Okay, so having that interaction between the two random factors did change a little bit. Once again, soil, still an interaction between the two, so really no big difference in soil, but what would happen if we did this one again? Yeah, okay. Not much is really changing if we do that way. So I don't really know the most appropriate way if we wanted to do the rep by year. So we're saying the interaction between rep by year is random. I think, and now you can see how these values kind of change here, and also their degrees of freedom. I don't know. I'm not a statistician, but those are the different ways of changing it. So just so you guys know. Okay, lastly, this is our model, but if we want to call our do our compact letter display, do our estimated means, this one's a little bit more complicated than doing the LSD test. So we have to say fit. We're going to call this fit. E means we're going to bring in our model, and then we have to call list pairwise equal to the interaction of soil and treatment. And I'm just going to put this here, adjust equals none. So the default is no adjustment, and this is calling Fisher's least significant difference. E means object, no variable name. Oh, well, What do you mean no variable name? Oh, that's why. Gotta close that out. Adjust equals. Okay, there we go. So now that's in the background. It gives us our fit. And now we're gonna call in, oh shoot. I think you guys also need to add in this library malt comp. So sorry about that. Hey, I'll kind of get that all together. And now we can finally do compact letter display. We're gonna call malt comp. So doing this like malt comp, I'm calling this package and I'm doing 2 semicolons saying within this package, I want to use the CLD function. I don't know if it's masked by another one, but it's just nice to do it. So we're gonna say take our information from fit emmeans and object equals fit emmeans letters equals letters. Okay, once again, we don't have it just yet, so we're gonna call our table CLD. There we go. So essentially what that's doing now is it's calling our entire model to give us these letter groupings based on the interaction. So you can see the difference between the confidence limit or lower confidence level. I have no idea what that stands for. Again, I'm not really a statistician. Hey, so mainly that's kind of what I wanted to get at is show you, how to do these mixed models. At least now you have the code to kind of implement it for other things that, you may be doing. So I'm saying we went through just the regular completely randomized design, randomized complete block design using the general linear models. So like type 1 analysis. We also did the strip plot or split plot design, which is a mixed model. And now calling it an lmerTest to do a true mixed model and type 3 analysis and to get those compact letter displays. This was kind of tough to try to finally figure that one out. It's easy enough to do the model. To actually get it to call and make a nice table is one thing. So finally, bear with me. So I'm going to do some adjustments in here. I just want to show you how you can grab some certain things. So, this is AF root rot index. Let's see. So if I'm doing my ANOVA, I have my model. Oh, that's all I'm doing here. So within here, I'm going to call my model again. And I'm going to say, I want the p-value for AF root rot interaction. So that's just for me, I'm calling it that. So I'm grabbing the p-value by doing the ANOVA model, similar to what we did up on top there. But when we run this model, I want to see here. When you run this model, you get, where did it go? Where did p-value? P way down in here somewhere. There's a lot going on. Anyways, just trust me. Is that the one? No, I can't find it. So we're gonna call the ANOVA, do the model, and then we want to grab the P R F I just want to see what happened. Okay, so let me run that model again. So here you see, here's our p-value. So I'm calling that column, the PR, greater than F. So if I run only this, it gives us these same values. So that's, this one, the 0.449. That's this one. We have this that's the second one. And here is the third one. So you see the third one is the one for our interactions or soil by treatment interactions. So we're gonna call the third p-value from there. And just to make it a little bit better, we're just gonna round that to 4 digits. Okay, so now if I look, I just made a brand new value here, the 0.0012. So that is my 0.0012 that I grabbed from that table. So if you add this in, let's say I'm only doing, I'd only want my interactions or like a nice figure for my interactions. You can add this piece of code in, just making sure you're changing AF root rod index. Let's say we want to go ahead and we do the rise root rod index. So I'll just do this as an example. You guys don't need to follow along right now. I'll give you this code later. Let's do rise root rod index. Oops. And once again, I'm just calling this as interactions, right? If I wanted to just get for the soil, I could do soil and then change that to 1 if you wanted to go through. So let's go ahead. Now that's everything for the rise. Where did it go? So, okay. So once we have, let's say we just want to make a table with those two things. I'm going to make a new data frame called p-value. I'm going to leave a column open for soil. And then in the second column, I'm just going to put p-value. And then I'm going to merge that one and that one. Right? So if we merge that all together, this links back to what we did our very first day, right? So pasting those together, making those strings. So where am I looking for? I'm looking for p-val. So p-value is a character with 4 different columns. Now, oh, did I mess up somewhere? Oh, shoot. Sorry, I did miss something. I'm sorry, this gets a little bit more confusing too. So, we called this compact letter display. When we run that, what do I want to do here? I want to, this is going to be a lot. Once again, I'll have this all for you, so bear with me. So what I'm doing here is I ran compact letter, or I did all my stats, and then I'm grabbing just the p-value for the interactions. Oh, whoops, round 4 digits. And now I want to make it a new data frame from my compact letter display. And I'm going to call that one, or an F. Once again, interactions, so I have the p-value, compact letter display. I'm going to use called dplyr to select soil treatment, just the estimated mean and just the group. So I'm going to drop out these other things. I'm going to round my mean to a whole number. Actually, let's do it to 1. Mutate. Okay, so then I'm going to group these together. And I'm going to rename my column. So instead of having estimated emmean, I'm going to call it AF root rod index. So let's just see what that does. Error not found. Let me get all this out of here. So now if I call just that, now you can see that I created a new data frame that has soil treatment, AF root rod index with our values, and then also our compact letter. And then I want to merge this together with our next one. So I'm just arranging it by soil and treatment. That way, when we merge them all together, they all align how they're supposed to. So I'm going to do that same exact thing now. I'm going to call that down here. Let's change this one to rise root rod index. Change my title to rise root rod index. Make sure all that runs. Okay, so there's my rise. Okay, now we made that p-value. And finally, we're going to use this other here. We're gonna take our first one. What did I name it now? I know this gets really kind of complicated or cluttered, I should say. So I'm going to take my first one here. That was with the AF root rod index, and super simple. Now I'm just going to call this left join from DPLYR, and I'm going to add in my rise root rod index by the columns soil and treatment. Okay, and then it's weird if you do this. Okay, so you look on the bottom now, it's like merge these two columns together and put AF and rise in the directly adjacent to each other. And then it's weird if you don't do this, you'll get a weird error. So I am going to mutate soil as character. And I'm also going to do the same thing to treatment. And finally, we're going to use rbind to bind our current one with our p-value. And lastly, type that into the cable. Oops. Whoa, what did I just do? Cable. And I just want my cable classic. There. So now we finally have a table here. We have our soil, our treatment, we have our AF root rod index with our means, our estimated marginal means from our mixed model. We have our letter groupings and combined with our rise, and then we have our p-values down at the bottom as well. So once again, this is nice. You can copy this photo directly into a presentation, but once again, you can also just copy and paste all this information and plug it right into a Word document so you can adjust some certain things. And that's how I do things now that I've spent the time to figure out how to do it. And once again, the reason I like to do this is it keeps things consistent. It streamlines the process. I don't know if you guys have ever had to do tables in Word, Excel, and then Word. It can just be very time consuming, manually getting means and standard errors and manually entering in the letter displays within each column. And so, hopefully with this date or hopefully with this code, you guys can take it, make some changes to fit your data. And I really hope that it helps you streamline your data in the future. So with that, I think that's pretty much what I wanted to cover. So I'm pretty happy. There's going to be some extra things. I'm going to send out my notes. I'm going to send out the entire, I'll send it out separately. So I'll do today's session. And then finally, I will send out my entire notes from all 4 sessions, all combined into one. And I also will link all these videos or send you the link to the YouTube channel that has all these videos. The ones that are on the Zoom will be deleted here after a couple months or something like that. So those won't be around forever. So I did upload them to YouTube, so you have those. So with that, Danielle, thank you for joining on Zoom. Hopefully you learned something, and thank you guys. Hopefully this will all help in the future. Thanks. Okay, I'm gonna stop recording. So I know that was it gets to be a lot. It looks really messy, doesn't it? Yeah. But now that we went piece by piece, did it at least help? No, I went a little fast.
You know, you've had the time to understand what KBL, cable, CLD, rename.
I'm calling those. Yeah, I'm making that. Right. You can name it anything you want. But it's like where you're fitting it, right? So I'm calling model, I'm just always calling as my linear model or mixed model, right? And then I'm calling ANOVA to summarize my model, and then calling cable to make a table out of it, or else it won't look good. Then we want to take estimated marginal means from our model, making fit, so then the compact letter display can take the fit to make the nice table that has the letters. Then we can take the ones with the letters, drop everything out, and make another nice table. Yeah, it's just like, I don't know, you get used to it. Nothing? Anything from you guys? Sam? Do you need anything for stats?
I mostly
Hopefully-
use my. Use that.
Yeah, but then you can't automatically make your tables and add all your columns. Yeah. So once again, just to emphasize like where I'm at right now, we do, 15, 18 trials throughout the summer. Actually, I shouldn't even say that, more like 25 or something like that. And a lot of them are all the same. And so this is very easy. Essentially, all that I do is copy my whole script, do find and replace, and I'll change assay to like the company name, the trial name that I'm doing for that one. Change it all. That way they have their own. Maybe make some other small adjustments, but it really streamlines everything. Then you can have all the stats done for that trial, move on to the next, all done for that one. Move on to the next, and then that one's a strip plot, so then I gotta change a bunch of stuff. Move on to the next, that one's a different one, so I gotta change a bunch of stuff.
Because one of the nice things about R is that you can avoid like starting somebody in a file. And you always have to say, this is file. Then it's easy.
Yeah.
Versus like in other languages where you can just, when you run it, specify the file, so you don't have to change it. Into like.
Sure. For the most part, you can keep a lot of things consistent, at least with doing this. And as long as so that also emphasizes just for you guys, I know, I don't know how you deal with it, but even in Excel, like trying to keep things consistent. I think that's been my biggest frustration is like year after year, I'm trying to figure out better ways of doing things or better ways to, name things. Because with my like Excel sheets, I don't want to have your first column is just your headers. There's no other information. You don't want spaces, you don't want numbers. So how to organize your data in a way that works well with R. And then year after year changing things and trying to make it better, which sometimes aren't really better. So then you have to go back and do things. So